In section 1, we really kind of waved our hands at and looked at this idea of area under the curve, and then we gave it a name of a definite integral. In section 2, we're going to more explore that and look at how did this come to be? How did this come to be? What is this big concept? How can we actually execute and evaluate it? Because really in that first section, we just talked about how we get to the point of this new notation or new symbols. We didn't actually evaluate, calculate as we go. Section 2 opens up with this idea of the fundamental theorem of calculus, and in this section it contains the most important and most used theorem of calculus, the fundamental theorem. It was discovered independently by Newton and Leibniz in the late 1600s, and it establishes your connection between derivatives and integrals and provides us a way of easily calculating many integrals, and was a key step to the development of our modern mathematics to support the rise of science and technology. Calculus is one of the most significant intellectual structures in the history of human thought, and this fundamental is the most important brick in that structure. And so this is actually not new for us. We've been using this relationship for some time. We just haven't written it this way. This says what we've said before. The definite integral of a rate from A to B is the net y units, the change in y, that accumulate between A and B. Here we've just made it plain that the rate is a derivative. And so what we're going to be doing is you're going to notice some notation here. You're going to notice that now we've written this as a capital F, and you can see that it was a derivative here. Then when it moves across this equal sign, we no longer write the integration and derivative. We're now working with the original function and plugging in the value of the b and a. So what we're going to be doing is we're going to have to take this stuff and move it backwards. And so let's just kind of look at this concept of starting with the derivative and moving backwards. If you remember from your derivatives in the previous sections, when we got a derivative of 2x, we were taking some power, we would bring it down out front and subtract 1 from it. So if we're bringing a number out front and subtracting 1 from it, when we go into the reverse, we're going to be thinking of adding 1 to that exponent and then compensating for that coefficient that was brought out front. So you may be looking at this one and go, oh, I know what this one is. This is just f of x equal to x squared, because this 2 was brought down and subtracted 1 from it, so this would be your original function. The problem with these is, if you remember from the previous chapter, if I had a plus 3 right here, the derivative of 3 was 0. So if I had a 31, its derivative was 0. If I had a 310, its derivative was 0. So working backwards, I'm going to have to take a little bit more time to figure out what's going on to figure out this constant. So until we get to that point, what we do is we just denote this as, you know what, if we're going to take this backwards and figure out f of x, we're going to call it x squared, but we're just going to say plus c, where c is just some constant of integration until we have more information to go with it. Because right now, until we kind of get our building blocks of how this is going to work out, we're not going to be able to find that value. But as we're moving and evaluating these, what you're going to see is we're going to change it. So you're going to have to switch your mindset. Instead of creating those derivatives, we're going to have to take those derivatives and move backwards. And so what is this called? This is called the antiderivative. An antiderivative of a function f of x is any function you can see as capital F of x, where capital F prime of x was equal to your lowercase f of x. So the antiderivative, we're moving backwards. The antiderivative of a function f of x is the whole family of functions, and that's why we're just going to write it as plus c until we have more specific information to go with it, where c represents any constant, and we just talked about that, how that constant, when you do take the derivative, goes to 0. So working backwards, we're just going to put a placeholder of plus c. The antiderivative is also called the indefinite integral. You'll notice that we are not defining from a to b like we did in the previous section when we were kind of looking at it. The notation of this is just the integral sign f of x dx, and this notation resembles your definite integral because the fundamental theorem says antiderivatives and definite integrals are intimately related. But in this notation, there's no limits of integration. The symbol is still called an integral sign. The dx on the end still must be included. And you can think of the integral sign in dx as left and right parentheses. This function is called the integrand. And so that's our bigger idea. And so I just want to kind of look at some of these antiderivatives, and then in further discussion, we're going to look at the exact way of calculating them. And so if it says find the antiderivative of 2x, I can choose any function I like as long as its derivative is 2x. Could pick f of x equal to x squared minus 5.2. It just said find an antiderivative of 2x. In the next example, it says find the derivative antiderivative of 2x. So I need the entire family of functions for the derivatives that are 2x. And so I would say the antiderivative of 2x dx would be equal to x squared plus c, because I want the antiderivative, not just one singular, but I want the whole grouping of them. And these are some of our easier derivatives that we faced in the previous chapter. Look at this next example. It says find the integral of e to the x dx. Well, if you remember this, remember e to the x was its own derivative. So it's also its own antiderivative. The integral sign tells me that I need to include the entire family. So I need that plus c on the end. I always like to, fondly think of that as Charlie. And so when I create this, I'm going to say, well, then that would be e to the x, and then don't leave off Charlie. You want to make sure you're keeping with your notation. If you are still working with your integral, keep your integral sign in dx. Once you have properly integrated this, then move on to that plus c. As we move forward and get to the end of this chapter, that notation is going to save you, because you can see which part is being integrated and which part you have already completed. So make sure, although homework is not being checked for notation in your steps, that you are practicing that notation to keep everything neat, clean, and orderly, but also so that you don't lose pieces. Because again, the end of this chapter, we're going to be doing multiple things in the same problem. And if your work is not neat, you're going to lose something, and it will throw off the rest of your problem. And so antiderivatives, graphically or numerically, another way to think about the fundamental theorem of calculus is to solve the expression for f of b. And so the definite integral of a derivative from a to b gives us the net change in the original function. And the amount we end up is the amount we start with plus the net change in the function. So what we can do is we can manipulate around that fundamental theorem of calculus. So this is just a restating of it. And this gives us values for the antiderivative as long as we have a starting point and we know something about the area. And so we are going to have some more values as we work with a problem like this. So let's look at some exercises and start evaluating some of these things. It says in problems 1 through 5, verify that f of x is an antiderivative of the integrand, and use part 2 of the fundamental theorem to actually evaluate those definite integrals. So again, we're still just in the shallow water here. We're just still playing with some numbers. We are not to the point of doing this whole process on our own, but we will pick up those building blocks in section 3. So it says, first verify that it's an antiderivative of that. And you can see in this first function, if I were to take the derivative of this capital F function, that would just be 2x. And so I can verify that f of x is an antiderivative because I can see that 2x here. Then we want to evaluate that definite integral with this function. So to evaluate it, what we would do is we would go back to our f of x function and plug in 0 and 1 and subtract those. So we would say, okay, let's plug in 1 squared plus 5 minus 0 squared plus 5. Evaluating that, simple calculations, that would give me 6 minus 5, and that would give me a value of 1. And so when you're actually looking at the definite integrals and doing that second part of the fundamental theorem, you're able to actually get a calculated value for the problem that you are working on. Let's look at this next one. Verify that it's an antiderivative. And we could take the quick derivative. Now, if you need some assistance with derivatives, you are still kind of confused over the last chapter, please reach out and let me help you with that, because you can see if you don't understand the derivative, you're not going to be able to take it backwards. So the derivative of this would be 3x squared, and so that is the antiderivative of this. So in order to do that second part of the fundamental theorem of calculus, we're just going to plug in 4 and 1 and subtract them into our original function. So 4 cubed plus 2 minus 1 cubed plus 2. Again, use your calculator, execute that, and then you'll be able to get your value. I don't doubt your calculations using either your handheld calculator or the calculator right underneath your problems, and you should get a value of 63. Just be careful with how you're entering it, keeping parentheses and subtractions. Let's look at the next one. Let's verify that it's an antiderivative. So to take the derivative of this function, I would bring the 3 down, multiply it times that 1/3, and that gives me a 1x squared. And we can see that is the function over here that we're trying to integrate. So we're just doing that second half of your fundamental theorem of calculus, and we're just plugging in. So we're going to say, okay, well, 1/3 times 3 cubed minus 1/3 times 1 cubed. Again, using your calculator to help you with this, should give you a value of 8 2/3. And just be careful, try to use exact answers where you can, instead of typing in 8.7 here or 8.67, go back and grab that either mixed number or improper fraction. And really your improper fraction would be better, especially with entering into your computers. And so really, let's maybe leave that as 26/3. But again, just using our calculator to help us with that. You can see for the next one, it's going to follow suit as well. Let's go ahead and check the derivative. And this was a 1/3 here. So f prime of x would be equal to, bring that 3 down. That gives me an x squared plus 4x minus 3. You can see that works out here. And again, we're just going to plug in. We're going to say f of 3 minus f of 0, plugging into capital F of x. And then you'll be able to get your value from there. Subtracting that, I end up with 18 minus -3. And so that gives me a value of 21. Now this last one looks a little bit trickier. You do have to remember your natural log functions, which I know some of you had a mishap in that last chapter on that one. The derivative of ln x is just 1/x. So I can verify that that part is true. Now you will definitely have to use your calculator when you come in here and do f of 5 minus f of 1. That would give me ln 5 minus ln 1. But if you remember your rules of logarithms from your algebra days, if you are ln both of these and subtraction, that would be actually ln of 5/1. So that actually reduces to ln 5. And ln 1, it's because that is 0 as a whole, and that's why it goes away. Now I am going to leave that as ln 5. I'm not going to run to my calculator, type it in, and round that 1.609. ln 5 is an exact answer, so make sure you leave it the way it is. So I hope that helps you with 3.2. And again, we are just kind of in the shallow end here with 3.1 and 3.2 and putting these ideas together, and we're really going to see a lot more working and figuring these out and giving us better building blocks as we work in 3.3. So let me know if you need assistance.